Okay, so welcome back after the coffee. So we're ready for the next session. And the first talk would be on building information modeling using constraint logic programming. And the speaker, Joaquín Arias, it will be online. So Joaquín, can you hear us?
Yes, perfectly. I hope you hear me.
Great, we can hear you. So please go ahead.
Okay, so thank you very much for the opportunity to present this work. The building information modeling using constraint logic programming has been already presented in CLP this summer. It's a joint work with Seppo, Törmä, Manuel, Carro, and Gopal, Gupta. So my name is Joaquín Arias. So let's start with a short introduction of modeling BIM models. So BIM is a methodology to represent 3D geometry and property like cost, material, or process of building as digital models. So each building, architect and engineer create a specific for each building. The stakeholders of the project create specific models, and these specific models must share and combine together in one unique model. So automated tools are needed to check the integrity of this unique model that we say that is a merged model from the initial ones. And in addition, this model must comply the regulations, norms, and laws that are applicable and may differ from one country or one state to another. So the design and construction of also of a building is a sequence of decisions, and we want to track this decision in order to check what is happening. So the idea is that automated BIM tools must combine geometric reasoning and symbolic conceptual knowledge. We want to reason in present of vague concepts and incomplete information. We will see more details about that in the next slides. And we want to deal with this ambiguity, which is present in regulations and standards. So the motivation and proposal of this work is that logic programming-based tools meet many of these requirements that we already discussed. So there are many examples that overcome some limitation of specific IFC-based tools that are used commercially. There are some query languages like Vim SparkQL. They are model checkers to check safety or acoustic rules, or like Vim RL that checks some rules. There are some translators for the building regulation. These examples can be in code. And also there is recent tools based on Klingo, which is ASP system, like similar to what we are presenting today, but has some limitation that we will discuss later on. So our proposal use tools that integrate constraint logic programming with ASP to model dynamic information and restriction in BIM models. So what we want at the end of this proposal is to shift from BIM verification to BIM refinement and to facilitate the implementation of new specification, construction standard, etc. We will see some examples in next slides. So as I told you, this work has been already published in CLP and TPLP. So we will see the reference later on. So the main contribution of this work is a framework which is based on constraint as well as programming that allows a unified geometrical and non-geometrical information. The prototype of a preliminary 3D reasoner under ProLaLa' with CLPQ and R. We will see that both are similar, and that we can evaluate with different BIM models. So then we provide an outline for an alternative implementation of this reasoner using SCASP, which is a goal-directed implementation of ASP, which overcomes some of the limitation on previous proposals. So the evidence of the advantage of our proposal is that it has the relevance property, which means that when we have a justification of a model, we have only the information that is relevant for the query that we perform. We'll see examples. We have justification for negative queries, so we can ask why something doesn't hold, and then we can make a representation and reasoning for ambiguity. So some background of BIM and IFC. So building information modeling combines the geometrical information with cost, material, and process, allows cost estimation, quality takeoffs, energy analysis, etc. And the final goal of this methodology is to make consistency of the digital models, which are shared with architect and engineer. And we want to do that through the life cycle of a facility, not only during the project or the construction, but later on during the use of the buildings. So UK also already requires level 2 of BIM maturity in any project. So here we see that level 2 is here, where we have a BIM model, and in the future we want to have more integrity and more feature of the working with this model. There are many authoring tools that are commercial and they are used by the industry, and all of them use a common data model to share the information between these systems. So some background of SCASP. SCASP is a goal-directed execution of constraint as well as programming without grounding, and provides constructive negations also for constraints. So here we have an example. We have a program where we say that the size of a room is greater or equal to 21, so we don't have to specify ground models. We can also define constraints. And when we make the negation, so we ask for the negation of this case, we have that one of the models is that the room is less than 21. But also it's important to notice that we have non-stratified negation, which is can be used to define different models. So here we have a small example where we say that a room is small, it is not big. So here we have something that is unknown. We don't have this information. And then we have, for this query, we have one model. So the room, we assume that is small, but we can also assume that is big. If we ask for the kitchen, which is information if that room 1 is a kitchen, we don't know what's happened about the other. So we only have information that is relevant for this query. So we will see the benefits of this relevance. And also we are able to specify classical negation. So we can specify that something is false, and we have evidences that prove these facts. And we will see that with SCASP and this relevance property, we will be able to generate justification tree also in natural language. So to define these vague concepts, where we don't know if it's one decision or the other, because we have ambiguity and we want to provide both possibilities, so we want to reason about assuming both cases, we will use these even loops that we saw before. So we say that the requirement for this law is that in the room there is at least one window, and each window must be wider than 0.6. But if the room is small, it can be between 0.5 and 0.6. So here we have the example. If it's not small, must be greater. If it's small, it can be greater than 0.5. So here the size of the room is a criteria, and in some cases, we don't know if it's small or bigger. But maybe we can specify, we will see an example, that for sure it is smaller than certain dimension is small, and if it's bigger than other, it's for sure big, but we don't know in between. So in this case, we will have both scenarios. Then with this information, we notice that we have to represent, since we are working with 3D objects, with buildings, we have to specify and to manipulate 3D objects. So we will use constraints in order to specify these objects. We will use linear constraints for this proof of concepts. Here we have a box, so we have 2 points, which are the vertex of this box, the lower and the higher one, and then we specify this element with this list of convex shapes. With these representations, we can specify, in this example, we have a 2D representation of 2 rectangles, and then we can ask for the intersections. So we have that the intersections is a convex that are greater or equal 3, but less than 4. So we have an X this dimension, and for the other dimension we have this greater or equal to but less of 4, and then we have this square. And in the case of the subtraction, which is the yellow one minus the blue one, we have this convex hole union this one. So we see that we have two convex shapes in a list, and then we have the constraints for this evaluation. So this is with CLP. What we are proposing is the use of SCASP. SCASP allows us to introduce the negation. So here we don't have to specify the whole execution of how to extract the intersection of the subtraction of the system. So we represent the convex shapes like constraints, and they are part of the constraint store of the program. And the representation of these objects are several clauses for each of the complex shapes. Then we ask, as before, which are the intersection and which are the subtraction. So we have, as before, one shape for the intersection and two for the subtractions. But here we see that to manipulate these objects, we only have to say that the union of two objects is the union, is the OR of these clauses. For the intersection, we have that these variables has to hold for both of the constraints. So we have the conjunction. Then we have the negations that in this formalism is for free. So we don't have to specify how to extract these elements. And then for the subtraction, we have that is the intersection with the negation of the second system, which is more or less a combination of these two clauses. So the idea is that using SCASP, instead of 39 lines of code that we had before, we have only 9 lines of codes that are these, and the operations are translated in logical operations, which is, in some cases, we will see that has benefits. Then, as I told before, what we want to do is to make something that is an iteration of models. So we want to reason about what is evolving during the definition or the construction of the model. So we want to consider the design process of a room and a safety norm, like below. So if we want to use a boiler that is fed by gas, the ventilation must be natural, and a window, the surface of the window has to be at least 10% of the area of this room. If the boiler is electric, we can choose between natural or mechanical ventilation. So this is the possible timeline during the design of this room. So initially, the model has no restrictions for the ventilation of the boiler. At some point, the architect reduced the size of the window, so the surface is less than 10%. So we have an alert. So the boiler has to be electric. At the same time, the engineer select that the gas has to be fed by gas for efficiency. So the ventilation must be natural. So we have an error. If we attempt to merge both models, there is an inconsistency. So the standard solution is to broadcast this error and to inform the engineer and the architect that something is wrong, but without information. So the idea is that what we want to propose is a continuous integration that determines who is the expert, whose opinion prevalence. So and only ask the other stakeholder to modify the proposal. So here we have an example of how it works. So I will skip this because maybe it's not relevant for us. So let's describe a little what's about the different model and how it works this and why it's relevant this the relevance, or when we want only the information that is relevant for the query. So here we have an example. So we have a hotel with 8 rooms. So we defined the rooms, and we have information of the site of 3 of them. As I told you before, if we consider that the room is less than 10 square meters, we know for sure that this room is small, and it's greater than 20, we know for sure that it's not small. So we have the classical negation. Here we specify this explicit evidence or against for generate the models. So it's small if we have evidence, and here we have the loop to consider in some case that is small if we have no evidence, or is not small if we have no evidences. And then we ask if the room is big or small. So for sure, for room 1, we know that it's big. In room 2, we know for sure that it's small, but for room 3, we don't know because it's in this area which is unknown. And for the other rules, for the other rooms, we also don't know which is this, if it's small or bigger, because we have no information. We don't have which is the size of this room. So we have this query, and we see that with SCAS, we only have 14 partial models for this query. And with Klingo, we have more models because it makes combinations that maybe are not relevant for the query that we perform, but they are in this model. The problem is that if we increase the number of rooms twice, then SCAS returns 30 partial models, but Klingo returns 13,000, more than 30,000 models, because this combination of the models that maybe they are not relevant for the query that's what we perform, which means that this exponential explosion in the number of models generated by ASP reduce the compressibility of the system. So when we make a query, maybe we are not able to understand what is happening. And here we see some examples of how it works when we make queries for this 3D geometrical representation. So here we have, for the first ones, that the rooms, that the doors are green and the rest of the objects are in blue. And this is for the whole program. And in Q2, this query, we constrain that the building is lower than -4 in this in this axis, but we want the doors that are between -7 and -4. So we see that these doors are here, and we can see without the rest of the building. Which is relevant in this query is that we can make queries with an unbound in the axis X and Z. So we can define slides. We don't have to bound the system because we are using constraints. So we can also make constraints as smaller as we want without modifying the program, which is one of the limitations of ASP systems. And here if we come, I mean, in these queries, we are selecting information. So in these ones and these ones, we are selecting objects from 2 different models. So here we have which are the object that intersects a beam from the other model, and here which are the parts that are not covered by the other one. We see that these parts are as small or as bigger depending on the representation of the building, but we don't have to modify the program. Here we have some values of how it's performed the our proposal. And here we see that the final benefits of our proposal is that we can generate these justifications, which are justifications tree for this query. So in the example that we saw about the boiler and the size of the window for the ventilation of the room, we have here the justification for the answer. So here is SCAS implemented using SUI ProLaLa'. And last year, when we presented this work, we launched a new playground using Xiao, and here we see the justification. So we see that the valid data for this information is that the ventilation of the system must be artificial, and here we here we see which is the justification for this results. So to conclude, I think I'm on time. So we have highlighted the advantage of a well-founded approach to represent geometrical and non-geometrical building information, including a specification, code, and guidelines as digital models. We can handle change to the model during the design, construction, and/or facility times, removing, adding, on change, object, and properties. And the use of CLP, and more specifically SCAPs, makes it possible to realize common sense reasoning, including geometrical data, and we can represent knowledge involving vague and unknown information. So for the future, we want to ship, as we saw before, from beam verification to beam refinement. So we want to check when we make a modification what was decided before. We want to develop non-monotonic model reasoning methods. We have to realize that usually in refinements, what we want is something that is monotonic. So when we make a decision, we want to continue to refine these specifications. So when we defined or designed a building, we need to modify some conclusion, some decision that we made before, and then this means that the refinement is not monotonic. And finally, we would like to integrate this logical reasoning in BIM software. And with that, I conclude my presentation. So I would be like to take any questions.
Thank you very much. So we do have time for some questions. Anyone in the audience? Anyone online? I do have a question, Joaquín.
Yes.
So a really nice talk and really nice integration with the existing tools. How are you dealing with the problem of incomplete information about the system? I mean, if they don't specify what kind of cooker there is in the kitchen, do you have rules for what is expected to be in the model, or?
If you don't, if you don't provide the information and you make a query, you may have different answers because the system will assume different scenarios.
Yeah, but what about warnings? I mean, do you get a warning that you perhaps forgot to specify if it's a gas or electric cooker, or?
Not really, because in this scenario where you don't say what you want, the system assumes that you will select which is somehow comply with the norms. Or maybe you can specify that if it's not provided, you get a warning. You can also specify that there is a rule which say that at certain point of the design process, you have to specify which is the method. Which kind of boiler you want to use.
Yeah.
So you can't. In any case, with this system, you can specify the rules in the way that you prefer. So yes, it's a very nice. Also, there is a. I didn't thought about that, but maybe it's a very good warning to say that if at some point you didn't provide this information or you didn't check that what is assumed by the system is what you expected, you can get an alert. That's right.
Any questions from the room?
And by the way, here is the.
Okay, nice.
But it's also in the program of. It's in the system. I provide the DOI in the program, so you can check the details of this paper.
Thank you very much. I have more questions, but I will ask them offline. So let's proceed to the next speaker.
Okay, so thank you.
Hand again to the speaker. Thank you.